Okay, this is the lecture yesterday. We have studied about electric field from chargers, one chargers, two chargers, and many chargers here. So the electric field satisfies the superposition principle. Okay, if we have n chargers, and then we just sum it, yeah, all the electric field of each charge, and then become a total electric charge or electric charge. Electric fields. Electric fields of the system. Yeah. So this is the form. Yeah. So in general, we have a discrete case, but if we can take n goes to infinity, it means that there are so many particles, then we can approximate the discrete case to the continuous case. Okay, so this is the continuous case. Continuous case. Yeah. So today we will discuss about continuous case. Continuous case, continuous charges.
Excuse me, sir.
Yes.
Are we going to bahas example that we last yesterday?
Maybe on Friday, maybe, but not this Friday, in the tutorial time. So I have to make it quick because we have limited of time to deliver the lecture.
Okay, thank you.
Thank you. Just remind me if you want to discuss it on Friday, but not this Friday, okay? Not this Friday.
All right,
so,
sir.
Okay. Anyone usually I announce this week, for example, this Friday, there is no lecture, okay? So you don't have to ask me again whether there is a tutorial or lecture, something like that. Okay, so, okay, we continue with continuous charge. Continuous charge. Okay, the simple case is a road, uniform. I'm sorry. Oh yeah, before we discuss about it, as I said yesterday, that the electric field of the continuous charge is K integral dq over r minus r prime to the 3, and then this is the vector, the direction, okay? dq here, we have lambda dx. Lambda means that density, charge density, per length. And then we also have sigma dA. So this is charge density per area. So this is area, dA is area. Sorry. Okay, and then there is also rho dV. It means that charge density over volume. Okay, so if we have, sorry, if the body is what do I say? If the density, maybe this density. If the density is distributedly over, I mean charge density, charge density. It's similar to the mass density. If the charge density is distributed all over the body, then the body or the system is said to be uniform. So what does it mean to be uniform? It means that lambda, sigma, rho constant. Okay, so we simplify the case. Mostly we will discuss about this uniform case here. So the body or the particle or the things, box, sphere, rod, disk is uniform. Yeah, it means that the charge density is constant. So the simplest thing is the rod, uniform rod. It means that this lambda constant. Okay, so usually we simplify the case. If we discuss about the rod, we only consider about the length. L, for example, the width is omitted. It means that we omit the width, means that the width is much less than L. Okay. So this lambda constant, okay, and then we can put this rod, for example, in the coordinate system like this. Okay, this is L here. And then we want to consider, for example, just for simplicity, we consider this the point A here outside the road, and the distance with this between the tip of the L here, this point L here, so this one is A, so this is A plus L, okay? Is there any question about this setup? If not, I will continue. So if we consider this infinitesimal charge here, the length is dx, the length is dx, So the distance between this axis is x, we call it. So what is the source coordinate? The source coordinate in this case is x, yes, and the field coordinate here is equal a plus L. Okay. So if you want to consider this, let's say this point P here, yes, then EP infinitesimal equals to K dq over R over to 3 and then this one. So this is, we can divide it by this one, so this we can slash it becomes 2. So this will be K dou Q over R minus R prime squared. Okay, this equals to K lambda dx over A plus L minus X squared. Okay. So if we want to know about the total electric field, we have to integrate this one because lambda is constant, so we can put this outside the integral. This is dx, a plus L minus x squared, and the bound is the lower bound is this one, yeah, the root. This is 0 to L. Okay. Any question about this one before I execute the integral? Any question?
Sir, so
Yes.
so the upper and lower bounds of the integral will be the rod length, yeah?
The road, yeah, the road between 0 and L.
Okay.
Because X here is the source coordinate. So the source coordinate, we only consider this area, I mean this road between 0 and L. Okay?
All right, sir. Thank you.
Okay. Any question? Okay. As you know, this integral should result, yeah, let's say this is 1 over minus 2 plus 1, a plus L minus x minus 1, sorry, let's say minus 2 plus 1, this is 0 from L. Okay, so this is minus K lambda. K lambda. This is 1 over A plus L minus 1 over yeah, just a moment. Yeah, A plus L. Okay. Oops, yeah, I think that's correct. Yeah. No, it should be positive. Yeah. Okay, that's correct. Okay, so this is K lambda over A minus A plus L. Okay. So the Q here, the Q total equals Q is integral from 0 to L lambda dx, and this is lambda L. Okay. So if you simplify the equation, the statement, so this should be K lambda A plus L minus A over A times A plus L. So this is K lambda L over, this would be Q over A plus L. Okay, that's the electric charge, electric fields. Sorry. Any question? So this is uniform road. Yeah. The first example. The second example is a ring. Uniform ring. So uniform ring like this. It has a radius R, big R, for example. Yeah. Lambda constant. Okay. So we can put, the ring in three-dimensional coordinates. This is the right hand coordinate, yeah, x, y, z. So we put the ring. That's bad. Let's say this one. So we have a point, for example, this is P here, and this is A. So this is origin, and this is A. Okay. So if we want to consider the infinitesimal charge, let's say we put here. The Q here. The Q is lambda, let's say dl. Yeah. This, if we looks like this, we put from the above, from the top, from above. This is like the R here. It's equals to d theta, r d theta. So d theta here is the angle, the angle here. The angle d theta. Okay, so this become lambda r d theta. Okay, because this is a constant, so Q we can directly see that this is a 2 pi r. Okay. Okay. So we have to identify the source coordinate, the source coordinate here, r prime here, is in the xy plane, okay? This is x prime plus y prime j. Okay, and field coordinates, it's a k. So basically this is, this is this r prime, okay? And this is r. Okay, so we have this, the infinitesimal electric field. This is k dq over r minus r prime to the 3 r minus r prime. Okay, any question? Oh yes, this r prime here, we could write it Muhammad Hamadi. What happened to Muhammad Hamadi? Is there any problem with the connection, the internet? Celine, can you ask?
Okay, sir.
Okay, let's continue. So this r prime, we could express in terms of r and theta. This is r cos theta I plus r sin theta j. Okay. Is there any question?
I have a question, Pak.
Yes.
On the diagram, the square represents a continuous electric field, right?
In the diagram.
Yeah, this square, labeled DQ
Square.
on the very left.
This one.
Yeah.
Okay.
And then
Yes.
in the calculations, did you calculate it as if it was a point charge? So you
Yeah,
made,
I mean this infinitesimal, we could treat it as we can thought it as a point charge. This infinitesimal charge, you mean dq.
yeah. How do you why can you why is it possible to have a continuous area of charge and then treat it as a point charge?
No, because we have a ring. We have ring. Do you know ring?
Okay.
Cincin, cincin.
Oh,
It's a continuous charge.
okay. But you can still treat it as a point charge, yeah?
Infinitesimally, yeah.
Okay.
In a very, very small scale.
Okay. Thank you.
Yeah. Okay, where do I begin? Okay. Just a moment here. Okay, if we consider this one, let's say I just write r minus r prime, okay? It means that we have minus r cos theta I plus sin theta j plus this one. Okay, so if you consider this r prime modulus, the magnitude of this factor is equal to square root r squared a squared. Okay. Okay. So if we have this one, so the order becomes 3/2. Okay, you can see that it doesn't depend on theta. Okay, so this dE k lambda minus r cos theta I plus sin theta j plus ak over a squared d theta. Just a moment. There is r here. Yeah? There is additional r. Okay. Okay. Then we can integrate. So we can integrate. So the total electric charge we integrate from 0 to 2 pi with respect to d theta. Okay. So you see that this part, for example, integral 2 pi cos theta d theta equals to equals to
0.
yeah 0. This 0. Also sin theta, yeah. 2 pi sin theta equals d theta equals 0. So these two part here 0, right? According to this integral. Celine, there are two in the waiting room. Have you already asked why they are late or they are having a problem with the connection?
Hadi said that pas nunggu kelas dia ketiduran, Pak. Kalau Muhammad Hamadi.
Okay.
Who's the second one, sir? Is it Zahid?
Second, Zahid Azmi.
Oh, kalau Zahid, he keeps reconnecting. He has a bad signal.
Okay. Okay, so we are left with K lambda 0 to pi a R d theta over A squared plus. Okay. So this should be K lambda R 2 pi. This equals to, so the total charge, as I said before, is this one, right? Lambda 2 pi R. So lambda 2 pi R. Yeah. So this is K Q A over A squared. Okay. So this is, okay, so this is the electric field. Any question? So this is the direction, yeah? The direction of the electric field. Electric field, yeah. So it means that the total electric field going only to z axis, positive z axis. Okay, this electric field, because it's proportional to the unit vector k, it means that each of these infinitesimal charge cancel to each other, yeah, in xy components. So we have only the z component. Okay. Any question? If you take the limit, a to the infinity. Or I can say that a, which is the distance from the origin, the center of the ring, to the point B, it's much, much greater than the radius. It means that. So, if we take this limit, this vector field will converge to K A to 3, this one. So this will be cancels, becomes 2. So this will reduce to K Q A squared. This is, let's say, sorry, this is 1 over P over 4 pi epsilon 0. So what it mean? This one. Muhammad Fazal,
Yes, sir.
can you explain what is that? What does it mean in the underline?
In the underline,
Q over A squared.
the Q over A square means there's a charge over a specific area, sir, for the Q over A square. Is that what you meant, sir?
No. What this formula tells us.
Oh, okay. There, it tells us about the electric field on a uniform ring, which we can infer from the
Okay, Humam Putu.
okay.
Is it mean that the bigger the area will have the smallest will have smaller charge?
Vanes Livaldo. Vanes, tidur deh. Are you sleeping?
No.
Okay. Can you tell us what does it mean? Q over S squared.
The more the distance, the less the electric field.
Cynthia Rida.
Iya, Pak.
Can you tell us about this formula, this reduced volume formula? This Q over S squared. What does it mean to us? What does it tell us?
I'm still processing. Is that okay?
Okay. Andi Nabia,
Yes, sir.
can you tell us about this formula? Sorry. What does it mean? We take the limit A to the infinity, or A much greater than its radius.
Is it the area, sir?
Sorry?
The area, sir.
The area.
Oh, it's the radius.
Okay. Okay, thank you. So it means that if it looks from far away, if the observer, or we the observer, looks from far away, it means that the ring looks like a point particle. Okay. In far away, sorry, far away. The rings looks like point charge, okay? Q over S squared is the electric field of point charge, a point charge, right? So it means that if we took far away, the electric field, we will measure the electric field exactly the same as point charge, even for ring. I hope that's clear for you all. Is that any in mind question?
I still don't understand, sir. Can you give us illustration?
Illustration. So if you for example, the ring, for example, the ring, for example, you see from well, it's not far away. If the ring in your hand, for example, is the shape of these things, of this body is ring, okay? And then you put, for example, 1 kilometer, but you can see the ring, okay? Then the ring for 1 kilometer, it looks like a point to us as the observer, okay? That's the simplest thing I think I can explain to you. Okay, is that clear? I hope it's clearer for you.
Okay, sir.
Yeah. Okay. Road, ring. Okay. Okay, maybe I will explain about more complex example. For example, like this. If you have a road, this is R, this is L, and you take, for example, the point P is here. So this is A, for example. That's quite complicated. And also, for example, if you take the ring like this, and you take, for example, this point P here. Yeah, that's also, well, also difficult to, it's not so difficult. I mean, yeah, it's more step to explain this clearer for you. So I will leave maybe on Friday, maybe Friday next week, yeah, not this Friday. So you have to think about it, and we will discuss maybe if you have a question, how to derive the electric field. Yeah. The electric field on XY plane, XY plane. XY plane. Okay. So we have to discuss new subsection, maybe a new sub-chapters. Gauss law. So Gauss is a German mathematician, yeah. Well, mathematician, physicist, and also philosopher. But Gauss is well known for mathematician, German mathematician in the middle century, I think, 1500 or 1600, I forgot. So before that, I will give you an illustration. If we consider a point charge particle, let's say Q, big Q here, and then, so this, let's say this is positive. So we have the line force, the line of the electric field's line outward, okay, like this line, electric field line or force line, electric force line. Then we can make a surface like this. Surface. The surface is sphere. Okay. What is the area of the sphere? Is, for example, the radius is r, for example, from infinity, from the origin. The area of sphere is 4 pi r squared, right? So this is a closed surface, for example. This is a closed surface. Okay, so the Gauss laws state that the distribution, Gauss law, the distribution of electric field lines inside the sphere in the sphere is proportional to the charge here. maybe to exact statement, proportional to the density, the electric density. Inside the sphere. Mathematically, we can say that this distribution, this statement is related to, let's say, in our case, E times A is the surface, the area of the sphere, and then this is Q enclosed. We say Q enclosed, and because this is in vacuum, we have to divide it by permittivity, epsilon 0, vacuum permittivity. Okay, so you see that enclosed means that how many charges you cover if you made this closed surface, in this case sphere. This closed surface usually refer to Gauss surface. In this case, maybe there is in mathematics, there is also the notion, another notion of Gauss surface, but in this case, the Gauss surface is related to the Gauss law of electromagnetic, of electrostatics, this Gauss surface. So if you make, for example, this sphere here, this sphere, there is only one charge. Okay, so this so we cover only one charge using this sphere, this closed surface in general. Okay, so this enclosed in this case is equal to Q. Okay, so in this case we have A, this E times A is 4 pi R squared equal Q over epsilon 0. Then we get exactly Q over pi epsilon 0 R squared. So this is the formula of a point particle, right?
Yes.
So, yeah. So, and this is, it has spherical symmetry. Spherical symmetry means that our case, it means that depends only on R. R is the radial coordinate. So this is the indication, yeah. This E, the electric field E, has spherical symmetry. So it depends only on R, the radial coordinate. And this surface, this closed surface here represent, we will discuss later, this equipotential surface. Equipotential surface. So it means that the potential on this spherical surface is equals. Yeah, so it's equals to equals. I mean, it doesn't only it depends only on the radial. So if you take the electric field or potential, for example, here and here, they have the same magnitude. The same magnitude. Okay, I think that's for today's lecture. If you have any question. So the point particle, the electric field of a point particle has a spherical symmetry. So the Gauss surface should be a sphere. If, for example, we have a road, very long road, the symmetry is cylindrical symmetry. Okay. I will explain next week, maybe. Yeah? Just for another example for Gauss law. Any question?
But I have a question.
Yes.
May we have the recording of yesterday and today's lecture, please?
I will upload it to the YouTube. Today's video. You can watch it.
Thank you, Pak.
Yeah.